Hello, good morning, everybody. Can you hear me?
Hi, good morning.
Loud and clear.
Okay, I think we can give a couple of minutes, 1 minute or 2 minutes, to allow the attendees to come and join us before we can
Okay.
start. So now we have about 20 participants, inclusive the speakers. Okay. One minute before we can start. Hi, Prof. Lau. Congratulations.
Morning.
Morning. Congratulations for your professorship.
Oh, okay.
Yeah, thank you.
Oh, congratulations. Congrats, Prof.
Yeah, thanks
This
for all
open
the
for
teamwork.
makan-makan.
Waiting for MCO to over. First.
Yeah.
We from IEEE know first because of Dr. Lau. On the IEEE we did congratulate Prof. Lau.
Oh, okay. Is it
Yeah.
Malaysia chapter?
Yes.
Computer Society.
Oh, okay.
Okay, I think we can start now. Okay, welcome to the webinar partnership grants between the Universiti Malaya and Sunway Universities. This is a webinar conducted by two universities, basically. For your information, this webinar is recorded, so everything, conference, everything, seminars, everything that you presented on this webinar will be recorded. Okay. During the sessions, it is advised for the audience to mute the speakers. Sorry, not speakers, the mic. You don't have to mute the speakers. Okay, and not interrupting the speaker. But if you want to ask anything, you may raise your hands. Okay, so each of the speaker will be given 10 to 15 minutes. Okay, I will read some bibliography before we start the for each of the speaker. Okay. At the end of the sessions, I will give about 10 minutes, 5 to 10 minutes for each presentations to answer any questions from the audience. Okay. So let us start the sessions. Before we start, I would like to brief the research on this webinar. This is actually a research between University of Malaya and Sunway Universities. This is a partnership grant. This grant is actually started on June 2018 and going to finish end of this year. So for your information, for the attendees information, this is partnership grants led by Dr. Rafida Matno from Universiti Malaya and Professor Yao Kot Lum from the Sunway Universities. Okay. So the title of the research, okay, Smart and Security Enhanced Transportation Ecosystem for a Future Sustainable Smart City Framework. This is related to transportation ecosystem. So before we start for the presentation for each of the speaker, I would like to read some of the briefings for the research. Okay, for today, the traffic congestions and safety have become vexing and complex issue in many urban areas. Okay, so traffic congestions are bound to occur at traffic hotspots such as intersections, public transport stations, and central business district, as well as when accident occurs. Okay, this issue actually uh, faced by many urban cities, causing problems that jeopardize the sustainability of the cities. So basically, we need to have an efficient transportation ecosystem, provide smooth and efficient traffic flow, reduce the road accident and greener environments, which for the future to then improve economic competitive. So basically, this research actually aim to improve the traffic safety and to improve the traffic congestions in order to reduce the prolonged traffic travel faced by commuters, particularly during the peak hours. So the scope of this research is actually the transportation ecosystem, as the commuter itinerary may consist of several separate legs. Okay, the goal of this research basically have five sub projects, and the sub projects are led by Dr. Lau, Professor Lau Sian Lun, Associate Professor Dr. Maizatul Akbar Ismail, Dr. Nojihan from Universiti Malaya, and then led by Dr. Richard Wong from Sunway University, and finally another sub-project led by Professor Yao Kok Lim from Sunway University. Okay, so before we start, I would like to read some of the bibliographies for all of the speakers. Start from Associate Professor Dr. Rafidah Matno. She is currently an associate professor with the Departments of Computer Science, Computer System and Technology, Faculty of Computer Science and Information Technology, University of Malaya. Currently, she had the Central of Mobile Cloud Computing Research, and currently also hold positions of Deputy Dean Science at the Institute for Advanced Study, University of Malaya. Her research is related to a field of transportation system in computer science research domains such as vehicular networks, wireless networks, network mobility, quality of services, and Internet of Things. And then we have another second speaker from Sunway Universities, Professor Dr. Lau Sian Lun. Okay, he is currently the head of departments of computing and information Sunway Universities. Okay, his research interests include ambiguous computing, sustainable smart city, contact awareness, and applied machine learning. Okay, we have the third speaker, Associate Professor Dr. Maizatul Akbar Ismail. She's from Universiti Malaya, currently an Associate Professor at the Department of Information System, Faculty of Computer Science and Information Technology, and served the Deputy Dean undergraduate at the faculty. She involved in various research, leading to publications of numbers of academic research in information system, particularly in semantic webs, educational technology, recommender system, and data mining. The fourth speaker, we have Dr. Richard Wong Tek Kin. Okay, he is a member of the Energy and Power Groups in the Departments of Engineering Science at the Sunway Universities. His research interests include smart transportation system, operational optimizations for sustainability, and embedded system applications. The next speaker, we have Dr. Nojihan Abdul Ghani. She is currently heading the Information System Department at the Faculty of Computer Science and Information Technology, University of Malaya. Her research interests include database, security and privacy, digital image processing, okay, data security, information system security, authentication system, and data security. And finally, we do have Professor Yao Kok Lim from Sunway University. He is currently a professor at the Department of Computing and Information Systems, School of Science and Technology, Sunway Universities, and his research focused on the applications of reinforcement learning to improve a diverse range of area from cognitive radio to traffic signal control, 5G communication in smart city. Okay, so I think I have briefed some the biodata from the speaker. Let me check what the this next agenda. Okay. So without further ado, I would like to invite the Associate Professor, Dr. Rafidah Binti Makno, to brief the research and to start the presentations.
Thank you, Associate Professor Dr. Badrul. I would like to share my screen now. So I hope everyone can see my screen right now.
Yes, I can see.
Okay.
Yes, it is you.
Assalamualaikum, and very good, good morning, everyone. My name is Rafida from Faculty of Computer Science and Information Technology for this particular collaboration research, or we call it as a partnership research grant between Universiti Malaya and also Sunway University. The members of the project consist of, from Sunway University, we have Professor Yao, and from we have Dr. Ismail Ahmedi, and my RA or PhD is Mr. Muhammad Asif Hussein. So my presentation topic is relevant to spectrum sensing in cognitive radio VANET. So before I start, I would like to share some content of the presentation. The first would be the description about the partnership grant, which which I'm the head of the project for Universiti of Malaya, and also some basic concept of cognitive radio VANET and our proposed architecture, simulation and results. So basically, the webinar talk is based on the paper that we're going to submit sometime this year, end of this year or early next year, which is a technical paper related to machine learning based cooperative spectrum sensing in dynamic segmentation enabled cognitive radio vehicular network. So basically the partnership grant, which as the moderator mentioned, it started in June, mid-year of 2018, which consists of 5 sub-projects and 5 leaders from Universiti of Malaya and also Sunway University. So we have the first sub-project is relevant to understanding the commuter's perception, meaning the behavior of the user, public transport, and also their perception related to integrated public transport system. That would is a one sub-project relevant to information system and also user behavior. And then we have the second sub-project is related to the IoT technologies improving vehicle technology. So we have an expert from and also from Sunway University to work on this particular sub-project. The third sub-project is relevant to the predicting real-time traffic information for the FAST solution, which is aimed to look at the real-time traffic planner system based on the mobile edge computing, which is to detect any anomalies among traffic flows. So we have an expert from sub-project 3 from SU and also from Universiti Malaya. The sub-project 4 is relevant to utilizing data anonymization for protecting personal data applied to traffic information monitoring system. And last but not least, we have sub-project 5, which is relevant to energy efficient cognitive radio based communication system, which led by myself and also Professor Yao. So basically, this is an overall architecture that we try to integrate all the sub-project into one particular idea, which is the improving transportation ecosystem for the future sustainable smart city. And all of the representative of the sub-project will share their research findings in this webinar presentation. So let me share with you on my part relevant to the cognitive radio in the transportation ecosystem. nowadays we find that road accident, traffic congestion reduction, infotainment, and many others are relevant to the intelligent transportation system, which is ITS. And ITS also consists of vehicle ad hoc network, which is another set of mobile ad hoc network. So from Intel publication, it says that in the coming years, the autonomous vehicle will be flooded with a lot of data, where 4,000 gigabyte data per day from autonomous vehicles, which is 4 terabytes. So with this particular flood of data from one particular vehicles, imagine that how the network bandwidth can support these crowds, as we can show something similar with what happened on the road lane in our country or any countries in the world if this has happened. So vehicle ad hoc network use a dedicated short range communication, which is the standard, carries 45 megahertz spectrum band at 5.9 gigahertz. So whether this channel is enough to serve all the vehicles on the road? The answer is no. So looks at the concept of ITS, Intelligent Transportation System, is an innovative services relating to the different modes of transportation and also traffic management. And we also have a concept of Internet of Vehicles. So it's also a sub-umbrella of IoT or IoE. So it's an integration of the three networks and inter-vehicle networks, intra-vehicle networks, and also vehicle mobile internet. In this concept, we also look at the cognitive radio, where we have the primary user and also secondary user. So we just imagine that you as a primary user, you are assigned with amount of bandwidth allocation, but sometimes you may not use your bandwidth, meaning that you are not utilize your bandwidth. So how can we share that bandwidth to the secondary user? And by using that, we can use, to share the bandwidth, we can use dynamic spectrum assignment, which is a spectrum efficient technique, where the spectrum can be dynamically assigned to the secondary user. And we also need to look at the cognitive radio sensor network, which is sensors of an event and collaboratively communicate their readings over dynamic available spectrum band in multi-hop manner to satisfy the application specific. So before we look at the cognitive radio, looks at the traditional radio concept, which it consists of the hardware, the RF modulation coding, and also the software is the framing and processing. So when the next version of a traditional radio is the software radio, where we have a combination of the hardware, which is the RF, and the whole modulation, coding, framing, and processing is a software. So we call it as a software radio. The third version of the third evolution of this radio technology, we have cognitive radio comes in, where we have a combination of hardware and also software. Inside the software, we have intelligence component, which is can sense, learn, and optimize. This is where we call it as a cognitive radio. So by putting the intelligence, meaning that we have the artificial intelligence family comes in. So in this work, we look at the machine learning, where we look at the sub-umbrella, the component of machine learning basic category. It is the reinforcement learning. We are looking at this reinforcement learning in our research work. So on the other hand, some spectrum are underutilized. As I mentioned, that if you are a primary user, but you are underutilize your spectrum, your bandwidth, how can we optimize the bandwidth? So the solution is to use optimized usage of underutilized radio spectrum through dynamic spectrum access, DSA. The enabling technology of DSA is what we call it as cognitive radio. So the concept of DSA is to allow the unlicensed user, which is in this particular, we call it a secondary user, to access the channel that are allocated to the licensed user for exclusive use, provided no harm interference is caused to the primary owners. Okay, so when the primary user want to use it, the secondary need to release that spectrum and allow the primary user to utilize the spectrum. So the spectrum sensing mechanism is a technique by which the SU find out the spectrum holes, which is the vacant spectrum that occupied by PO from the licensed frequency bands to access opportunistically. Okay, so this is kind of the idea, how can we shed the unutilized spectrum in the vehicular ad hoc network. So the processes of the cognitive radio or radio environment consist of the sensing, analyzing, reasoning, and also adaptation. So in order to do that, there are some challenges in spectrum sensing, which is vehicle speed, the direction of the vehicles, the multiple fading, shadowing, hidden PU problems, the effect of the PU activities, the heterogeneous of the QoS requirement of different networks, other spectrum techniques that available, security issues. These are all the challenges that we find out from the literature in the beginning of our research project. So we find out from the literature that latency for any safety messages from vehicle must be less than 100 milliseconds, but in general, the average spectrum switching take times about 2 seconds. This is a literature from Michael 2018. So due to the following factors, to implement cognitive radio vehicular ad hoc network performance will be degraded if we want to do this. So this is because of the imperfect of spectrum sensing without proper environment knowledge of the network, high spectrum sensing errors due to the lack of global decision making. Cooperative spectrum sensing, CSS, is susceptible to the overhead issues because there are so many processes that we need to be done at the RSU. Considerable transmission delay due to improper network management and channel assignment. So from the literature, the shortcomings of the recent work on the spectrum sensing techniques for VANET involve all this. So by using the single spectrum sensing for all conditions leads to degrade of the spectrum sensing decision, makes the false alarm rate increases. By using the static threshold, which is not applicable because VANET, the nature of the VANET is dynamic environment. Improper clustering of the road segmentation because of the improper network management, skipping several significant parameters that proposed in previous work, and also all the CR functions, sensing, allocation, perform the RSU. RSU is something what we call it as a base station or any communication tower. So in VANET, we call it as RSU that creates latency and also data congestion. So from all the literature, from most of the literature relevant to the CR VANET and also spectrum sensing, main problems in CR, which we divided into spectrum management and also network management. So the lack of spectrum management, meaning that the vehicle as SU in CR VANET use conventional spectrum sensing technique, which is subjected to limitation. So this technique is suitable only for environment features, and the use of spectrum sensing technique also leads, with all conditions, leads to degrading of the spectrum sensing decision, which increases the false alarm rate. Meanwhile, for the network management in the CR VANET, the road link is segmented concerning its length. The road link segmentation is fixed and uneven. So vehicle traffic density differ from time to time, impacting abnormal detection of the spectrum and channel allocation. So before we show you our proposed architecture, so these are the important entities in our proposed model. The first one is RSU, or we call it as a base station. So the function of RSU to do the road segmentation and also to do the channel allocation. The second entities, important entities, is the vehicles. So vehicles on the road can do sensing. So we apply the spectrum sensing technique selection by using the fuzzy naive bias, and also to do the spectrum sensing by looking at the two important parameters, which is the dynamic threshold and also energy detection and mass filter. The third important entities is the SSA, which is a segment spectrum agent. We created an agent in the network to make a global decision making by using another algorithm that we improve the existing reinforcement learning algorithm by putting an agent in this algorithm so that the SSA can make a report generation. So basically what we want to achieve in this CR-VNet are two aspects: the accurate spectrum sensing and decision making, and also a stable network management. So we come up with a very huge or big CR-VNet segmented architecture, which I divided into two for this presentation. Basically, it's a combination between this slide with another next slide. So in this particular slide, to show that we have the RSU consists of the cognitive radio, CR-RSU, and we have the primary user here and also secondary user here, and the road is divided into two lanes, and this is the left direction, this is the right direction, and the road is divided into segment 1, 2, and 1, 2, 3, and so on, and we have the primary user at this segment and another segment. So from this diagram, what we want to achieve is we come up with a novel segment-based CR-VNet architecture, which we will segmenting the road lanes into equal distance by looking at the probability-based segment management. So we use probability value to look at the speeds of the vehicles, segment size of the road lane, and also the node degree. So we know that in each of the lane, the speed of the vehicle varies, and the density of the vehicles on each lane is also varies. We don't say that this is high density and this is also high and this is also high, but in the realistic environment, in the real world situation, sometimes we find this is very high density, this is very low density, and then comes again high density. So because of the dynamic situation of the vehicle IDOT network or transportation, we need some probability value to do that, to ensure that our threshold value is dynamic and is not fixed. So the CR-RSU also function is to do the channel assignment or the channel management by looking at the data type, the bandwidth, delay, and jitter. So the segment are managed to continuously by a probability-based sub-segment management approach. This is what we provide the solution, and each segment is further divided into the sub-segment on the speed, segment size, and the node degree. So the next architecture that so actually it's a one big architecture, but I divided it into two so that it's clear in terms of the presentation. We have the segment 1, 2, 3, and in the segment, this is what we want to achieve. The spectrum sensing accuracy is improved by dynamic selecting sensing based on the SNR, signal noise ratio, and also noise power. So in the segment, this is what we call SSA, segment spectrum agent. We created an agent, and this agent has a tri-agent reinforcement learning where three agents will look at will learn from three environments. The first environment is the signal environment, the network environment, and also the vehicle behavior. So, and from this SSA also will generate a report. We call it as a local or a report from each vehicles, and also to look at the presence of the PU, which is the primary user. And from this report, global report, we will forward it to the RSU to make a decision. So from here, we can see that the SSA will send the local report from each vehicle nodes, and these vehicles node use this dynamic threshold by using the fuzzy naive Bayes, okay, to make a decision from by using the energy detection and also mesh filter, and we combine this through to come up with the dynamic threshold. So the dynamic threshold value is introduced in this spectrum sensing so that the RSU can make a global decision. So the sub-segmented of CSS, okay, if we are looking at the I segment, so this SSA, which is the segment spectrum agent, the first one will send information to the each segment road, each segment of the vehicles about the existing availability of the spectrum, and to learn about all these vehicles, and each of the vehicle then send the local report to the SSA, and SSA will send this will make a data fusion to integrate all the report and send it to CRSU to make a decision. Then the CRSU will make decision by giving the allocation of the spectrum to each of the segment. So the solution is we want to reduce the burden of CRSU to make a decision where in previous work, CRSU will learn all this information from each segment or from each vehicles, and this will increase the overhead at CRSU. Now we remove all this overhead, we put it in the segment where this segment will, and we have 3 agents where they will learn about all the behavior of the vehicles, the network environment, and also the signal. So the global decision making by using the TARL based decision making, we have signal environment, network environment, and also vehicle behavior. The agent will collect all this information and make an action, and also at the end it will rewards to the SSA. So each of the agent learns about the SNR, channel quality, and also to learn about the agent number 2, learn about the global sensing, the sub-segment, and also number of vehicle, and agent 3 learn about the mobility and also vehicle ID. So we come up with a proposed algorithm. I'm not going to go through all this algorithm, but we have our own algorithm, and we also have a proposed CSS through the cooperation model, where we have parallel fusion model, user selection, we have sub-segment. For sensing, we use fuzzy naive based algorithm, where we look at the this is chooses the ED and MFD, as I mentioned before, the hypothesis, and so on. Okay.
Dr. Rafida, you have about 1 minute to finalize.
Okay. Thank you. Sorry. So I'm going to put it very fast. We simulate our idea using the OMNET++ with Sumo, Vins, and INET to evaluate our idea. And we have some results in terms of the probability detection, in terms of the speed of the vehicles. We compare with the energy detection, match filter, and also through other benchmarking. Some results related to the false alarm, whether the PU actually has is there any unutilized spectrum. We also look at that false alarm. So as a conclusion, we come up with a few novel idea, which is the segmented of CR-VNet, the sensing technique with use hybrid ML algorithm. We have combination of fuzzy and naive Bayes algorithm. We also propose dynamic threshold by using the probability value. And we have an agent that we propose embed in the reinforcement learning. So we come up with some novel idea in this particular work for 2 years work. So some of the publication that we have managed to publish is a combination between, because this is a partnership grant between SU and also We have published 5 articles, Q1 paper and Q2 papers. and articles under review and revise and resubmit and submission soon. We have book chapters and also some conference proceeding. By that, thank you so much.
Okay, thank you very much, Associate Professor Dr. Rafida. Okay, so we have about 1 hour sessions to go. I think without further ado, I would like to invite Associate Professor Dr. Who's the second presenter? Dr. Professor Dr. Lau Xian Lun to present his presentations entitled "The Using IoT Technologies for Improving Vehicle Safety." Okay, you may present your presentation, Professor Lau.
Yeah. So I hope you get to see the slides soon. Is it
Yeah,
working?
I heard some of the attendees mentioned that they can't see the slides.
Correct. Yeah.
I
So
hope
is
that
the slide visible since I can't see what you see?
the slides. And Dr. Shiva, can you see the slides? Because you did mention that you can't see the Associate Professor Dr. Rafida's slides. I hope that you can see now. Okay, Professor Lau, you have 15 minutes.
I'll make it short and sweet. Yeah.
At 10 minutes from now. Thank you.
Okay. Yeah. So I hope the slides are okay, right? Because I might got the wrong screen. Anyway, thank you very much for this opportunity to share what we have done in the second subgroup. And I've prepared something less in detail or technical, just to make sure that at least the overall idea and probably with the introduction of the whole concept might also invite further work together with anyone who is interested. But the whole idea here is within the big framework, we look particularly into how IoT will be able to help us to improve vehicle safety. And again, as introduced, I'm Xian Lun, and I'm from Sunway University. And I represent the subgroup with colleagues from Sunway University and University of Malaya. Mainly, I lead the team with Dr. Cha and Dr. Tahir and our student Muhammad Usama. And at side, we have Prof. Ms. Laiha and also Associate Professor Muhammad Yamani and Associate Professor Dr. Jiraj. So the motivation that I think we would like to go through is this thing. Driving seems to be something we think is easy if you have been driving for quite some time. But the little that you notice, if you remember back to your first 2 months of driving a car, is actually a highly complex situation, because not only you need to manage the vehicle, you also need to pay attention to the environment, and there little chance that you should be distracted, right? And all this thing has to do with what I want to show next, that if you look at driving, it's never about yourself. You have this whole environment, and today, driving in big cities is even more complex. I always joke when I come back to Malaysia many years ago, driving in KL is very scary, because the moment you take the wrong turn, you end up driving somewhere for another half an hour to 1 hour just to get back. And during this time is usually crucial, because the moment you panic, you're unfamiliar, and again, that's where you may put yourself and even other drivers in danger. So the question comes back to, are the vehicles not smart, right? They should be smart enough to protect us, right, from any of this danger. And you can see these are not the most high-tech car. Maybe the most expensive is, okay, lorries are expensive, but if you talk about cars that we usually buy and drive, Mercedes may be the expensive ones. But they seems to be still quite conventional, right? They are not like those that you hear today, like the Teslas, the self-driving cars that seems very high-tech. We know one day that will be a norm, but until that, right, that's the period of time. And again, without going to a self-driving car, can cars be smarter, right, that can protect us and save us from any of this danger? And coming back to the two pictures, you have trucks or vans. They are really the kind of vehicles that will have to travel every day to bring products from point A to point B. And you can't neglect the fact that they too need this smartness. Imagine, I used to talk to some truck drivers, when we ask them how is their job, and they have to drive long hours, 6 hours, 8 hours from point A to B to transport things, right, from cities to cities. They too need this kind of security, safety measures that their vehicles can, operate safely. So a bit of statistics just to tell you how important this area can be within the big framework and also in our subgroup. You can say that in US, these are the statistics I managed to pull out, that you can see many of these traffic accidents actually will end up, some of them end up as a fatality, means people lose their lives. And many of them has to do with human. You have speeding. The scenario I just mentioned about large truck, you have at least about kind of 14% that's due to large truck crashes. And that reminds me, whenever I drive near a big truck, I always get very frightened. You don't know who will knock into each other, right? And coming back to Malaysia, the statistics from our Department of Statistics, again, the latest I can pull out is from 2018, where you can see very large number, and how many has some casualties. You can see about 8,000 have injuries. You may say compared to 548 is not big, but you are talking about at least 8,000 reported cases that are having injury, and there are also 6,000 cases that are deaths. I don't think they overlap, so you have that kind of 14,000 too that could have been avoided and saved people from injury and deaths. And that brings us to the motivation. What can we do to make even current cars smarter? And that's where we want to look into this possibility where can we equip cars, right, with sensors. And from the work from Guerrero Ibanez and colleagues, in 2018, you can already see a car can, right, be equipped with all these different sensors, such as GPS, you have videos, right, microphone. You can also put in radar sensors, infrared sensors, and so on. And there are things that allows the car to know what's happening, right? And then is this something we have today? That's the question. How many of us drive a car that we ask, can this car already give us some of this information? Or do we need to equip these cars with these sensors so that we can now do all these smart things? And on top of that, other than the sensors in the cars, you can also look at sensors around the environment. For example, in the same paper, if you're interested, do look up, right? And they analyze and share that you can also put sensors along the road, for example, that from radar sensors to cameras, and also even with laser beams, so that you can do things like counting, checking the traffic, and so on. And I think the one that we should really look into is really the cameras, right? Where it's not something too new. If you look at Singapore or China, these cameras that do real-time analysis, right, are used in order to track what's happening on the road, okay? And also, this is how we use such sensors to help to bring safety or improve safety. And one more thing that we should not ignore is we do carry a sensor around us every day, right? If you don't notice, the smartphone you and I carry, and some of us have even 2 smartphones, is actually an amazing sensor device. And there are even work that they use a smartphone to detect how the car is moving. I did check and read some work like companies like Uber or Grab. They are also equipping, right, their drivers with a smartphone app. And those smartphones are also tracking movements that can be used to check how well someone is driving and so on. So you can see by using sensors, we can now sense and understand things that normally as human we may see. And even now, if we can't notice them, these sensors are helping us as additional devices that can understand what's happening in the car, around the car, and we want to use that to improve the safety. So coming to the sub-theme that I would like to introduce, what we do is we hope to investigate, first discover, and then investigate suitable techniques and solutions that can allow vehicle technology to have the awareness to improve vehicle safety. Awareness actually means, can the car sense things just like human? We don't do that so well because we cannot really focus on too many things, but the moment we can, we do sense a lot of things. That's why driving itself is a skill that you can see as you go on years. You tend to be able to sense what's happening even though you are looking ahead. And how do we bring that kind of awareness and ability to a vehicle or even the system around it? And that brings in ideas like, can IoT, AI, or even blockchain be equipped? So this picture itself is something, even I think some of us have started working in vehicle safety or pedestrian safety, that you can see is a big environment. So in the previous talk, Prof. Rafida already showed how the big picture is like, and now we are looking partly from the vehicle point of view. Wait a second, just give me a second. All right, sorry for that. So the research question we have here in our work, right? We are talking about what kind of data can we acquire from a normal vehicle today? And when we can get this data, then that gets interesting. What can we do, right? This data can be acceleration, it can be the movement, or even how we deal with the pedals, okay? Or even all the way to consumption, usage, and all these things, how do we lead them to better safety? And we want to ask this question, what kind of artificial intelligence techniques? It can be ML, right? It can be AI algorithms, deep learning, that can be used to model this data, right? And more importantly, can we then derive to context? That's where we want to make things that not only the machines can understand, as a black box, right? If you know a little bit about AI, deep learning, many times now they are smart, but we don't really understand what are understood. We just believe that they are best decision. So if we can extract those things out and make them into not just machine, but also human comprehensible context, right? Situational information, that we also know how this machine understand and respond to this situation. That will be something really good, so that we trust and we also know how this vehicle really has behaved and operated. So let me go on. So a few things we have done within the work. Two parts. If you look at the left-hand side, we have at Sunway also some of these simulator setup where we get to use a driving simulator, and that's where we get to at least have some idea how a person may drive, and also we get the information from the pedal and so on. So that is partly necessary, because when we have started looking at the right-hand side, real-world sensors that we can get from the cars, we realize it's not as simple as we thought, right? So the simulator at least help us to get some of these insights, and also some simulated data that we can, work on the possible understanding and modeling first. And as we look into how to acquire this data from hardware, from the car itself, you can see the top are two devices we have tested. One is a kind of Bluetooth device that you put into the cigarette, right, adapter, where it provides the movement data collection. Secondly, the one on the left, if you can see my mouse pointer, a very small device, and it just directly fit into the OBD2 port, right, on modern cars, that allows us to also have access to real-time data of, let's say, acceleration, fuel consumption, and so on, and even braking. And all this gives us at least some ideas how such devices can already open up the data that typically is hidden or even unknown to many of us, right? And if you are new to this term called OBD port, it's actually a port that if you bring your car to services, today the car service center typically can attach their kind of diagnostic system into the port, and they can read what happened to your car, let's say the past months, or year, and using those information to now run diagnostic to understand whether your car is in a good condition or not. And we can also use this data through the same port and transport that to a mobile device, for example, in order to access the data either real time or collect them, and then use that to do our analysis. So you can see the one at the bottom is the one we actually now plan to acquire to use that, because the top two, even though they give you real-time data and some you can do some recording, but they are closed system that you can't really perform more tasks than what the company allowed you. And the bottom one is an open system that at least will give us some more access to the data. All right, so these are the two main approaches done.
You have 2 minutes.
2 minutes. Oh, I thought I'm fast, but actually I'm not that fast. Okay, let me go quicker now. So what kind of information and context can such system allow you to capture? With the few information I've mentioned earlier, like the car acceleration, movement, and even the pedaling and so on, you can roughly derive to some of these things. Is the person fit to drive? Is he tired? right? Is the driving behavior getting more dangerous, right? And how about the driving style? Is it something that may lead to possible danger? So you look at the bottom, does it possibly lead to danger? Is this person driving too fast, or even if any emergency will take place? And if we can capture all this information, that gives us the opportunity to react or act on it. So a very high level kind of understanding is, can the car, together with smartphone and also the sensors that we have, such as the movements, GPS, speeding, acceleration, the car condition, right? Is the car actually having some problem that you didn't know and may lead to some things that the system on the right hand side, I kind of simplify into a cloud, but actually that's where you have the machine learning mechanism, the models, and also the back-end system that can monitor not just one car but many cars, right, to lead to those conclusions or context. And by using that, we can then kind of make sense out of it and make the system respond and react based on this thing. So some ideas, like from the simulator, you can see the driving patterns for the speed or the braking. They may tell some kind of information that we would like to capture and understand using machine learning or AI. So I think I've kind of talked about this already, but the main idea is to make sure not only human can understand, the moment even we didn't pick it up or we didn't have that attention, the car is picking up things that we normally sense as human, and now pass that information to the system and let the system react timely. Yeah, so like I said, coming to the end, I think the vehicle safety is important, and we want to use all these existing sensors and even new sensors so that we can use AI models to improve safety. And all this should lead to not just a black box operation, but also contextual information that can help us to understand and take good action. And I think, without mentioning it earlier, but we hope this kind of technology can be part of the advanced driver assistance system, which is, I think, autonomous level 2, right? And maybe it may also go into autonomous driving and so on. I think that will be the long-term vision of this group and also others who wish to work with us on this area. Yes, I rushed through the last part, but I hope this gives you the insight of what we do in subgroup 2 and the big picture. And also, thank you very much for your attention, and stay safe. Yeah, pass the time back to Dr. Badro.
Thank you, Prof. Lau. Is there any questions from the floor? Okay, I would like to remind to all attendees, if you want to ask any questions, please do raise your hands. Not physically raise your hands, by using the icon in the Meet so that I can see your notifications, so that I can have your questions and then interrupt the speakers. Okay, I think without further ado, I would like to invite the next speaker from University of Malaya, Associate Professor Dr. Mazatul Akmal Ismail. She will be presenting the sub-projects, the next sub-project entitled the Understanding the Commuter Perceptions of Integrated Public Transport System. So I would like to invite Dr. Mazatul to take over the sessions. You mute, please unmute.
Okay, Assalamualaikum. Very good afternoon to everyone. So can you all see my screen? I can't see my screen on my screen.
Oh yes, of course, I can see.
Okay. All right.
Just make it full screens so that everybody can see it figures. Yeah.
Okay now?
That one nice.
Okay. All right. So okay. Oh gosh. Right. So this is for sub-project 1. Okay, so thank you, Dr. Badro. So I would take less than 10 minutes to present this, okay, because this is just sharing all the publications that we have, or some papers that are under review for our project. Okay, so our project is on understanding the commuter's perception on public transportation. So I'm leading this project on UM side, and from Sunway University. It's led by Associate Prof. Dr. Chua Huina. Right. So the first paper that we presented is sentiment analysis of user perceptions toward public transportation using Twitter. So what we found is that we focus more on Prasarana Malaysia Berhad, okay, where this is an urban rail services include 3 networks of light rail transit. KL monorail and also MRT. So the data that we collected is from January 2019 to April 2019. So the methods that we use to get the polarity or sentiments of the Twitter, we use SVM, support vector machine, where it shows the highest score for sentiment classification apart from the other techniques that we choose. So what we found from this paper, okay, is that there's two sides of user perceptions. The positive one is that the users are actually happy with the service, okay, in terms of the helpfulness and also the friendliness of the staff. And also the efficient complaint management, in the sense that when complaints are put up, there's quick response from the staff to actually improve or amend whatever that is being complained of. For instance, if the elevator is not working or the lift for people with disability is not working, okay, so they take quick action based on that. But most importantly, okay, the negative perceptions is more than positive, okay. So we divide these perceptions into two. First one in terms of service, okay, poor maintenance, malfunctioning escalators and lift, insufficient service during peak hours, meaning to say that they fail to schedule additional trains, okay, during the peak hours, okay, that cause service delay. So in terms of punctuality, there's variation of public transport arrival and departure time from the schedule, delay due to sudden incidents of train stop in the middle of journey. So this is the findings from our first paper that we presented early this year. Next one is on a paper that we presented on a seminar of information retrieval and knowledge management just recently. Okay, so this paper titled Contextual Based Term Weighting for Keyword Extraction of Transportation Domain. Okay, so why we come up with this paper? Okay, so this is the first part of the research where we found that there is no specific corpus on transportation area. So what we did is that we come up with a term weighting approach, which aim to convert text data to numerical representation, okay, so that we can do analysis. Okay, so why we need to put up certain weight to certain terms, okay, is because we want to make sure that the retrieval of information based on these data sets, okay, is accurate. Okay, so what the study do is that it proposed a new unsupervised context-based term weighting formula for domain terms extraction. So in our case, the transportation domain, and the test on collected transformation data set shows enhanced result over the traditional TF, IDF approach and also PMI. So point-wise PMI is also known as point-wise mutual information. Okay, so how point-wise work is that it try to find the match between the nearest terms to the terms that we actually look at. Okay, so in terms of the result, our techniques, okay, outperform the two previous approaches. Okay, the next one is the paper that we submitted to Science to Metric. Okay, so this is still under review, titled Investigating Transportation Research Based on Social Media Analysis, a Systematic Mapping Review. So the findings that we found from this paper is that what we do is we come out with a review on social media-based transportation research from 2008 to 2018, 10 years period. Okay, so what we found is that the most productive country and the most productive year, okay, for social media analysis based on transportation research is coming from the state of US, and also the highest publication is on the year of 2018. So social media data that can be used to improve transportation related issues, we found 3 terms, okay, which are the weather, time, and also location. Okay, other findings shows that most social media used for transportation research. The first one, the topmost, are Twitter, followed by Weibo, then TripAdvisor, and also Facebook. So why Twitter receive the highest is because the availability of the API for the data to be able to be scrapped, okay, according to the period that we want. So if you want to scrap certain data from Twitter, okay, free version provided you limited access. But if you pay a certain amount of money, you can actually access, okay, from the period that you want. Okay, and then we found that lexicon approach is widely used, okay, to find the polarity or the sentiment of the papers, followed by SVM and also Naive Bayes, okay. And I think one of the interesting facts that we found is that there's no research found on water transportation. So from our further analysis, we found that perhaps water transportation do not pose many issues compared to air transportation and also road transportation. So this is the findings. So we are still waiting for reviewers' comment on our work. The next one is the paper that we submitted to IIT's Journal of Engineering on challenge of mining Twitter data for transportation service analytics, specifically on Malaysian context. So this research, we focus on finding what are the challenge, okay, what are the issues that we face, okay. So the finding shows that the Twitter data can only be useful in generating reasonable insight if user could input informative words for forming discussed topic to derive opinion, especially the adjective words, okay, and inclines toward a certain sentiment through the use of adjective. So the findings of this paper also identified the need of a more proficient sentiment dictionary to classify multilingual tweets. So you know that Malaysia is a multiracial country, okay, so we have Chinese, okay, the topmost race, Chinese, Malay, and also Indian. Okay, so we have somehow mixed the language that you post on the Twitter. So this pose difficulties for us. Okay, so next research we are going to look at this Manglish tweets. Okay, so our research provide original evidence proving that the potential of using social media data to assess public transportation service, which may vary depending on the demographics of the social media users. Okay, so we found that social media users from urban area provide more informative tweets, okay, compared to the user from the outside of Klang Valley. Okay, so the next one, also under review, is the paper called Term Standardization with LDA Model to Detect Service Disruption Event Using English and Manglish Tweets. Okay, so the case of rapid transit service in Malaysia. Okay, so look at the example here. Okay, how it's very difficult to, okay, classify the sentiments of this data. Wei macha, you want to makan here or tapau? Okay, you can see that this is a mix of three main races that we have here. Okay, so from this, okay, what we intend to do with this paper, okay, is that we found there's 4 types of tweets. Okay, first one, in terms of opinion, the users are giving their opinions about the LRT services, or they're seeking for information. They want to know about the schedules, okay, or where to get the information about the train. And then next one is on complaint. Okay, they are not happy with certain service, okay, especially on the delay. And then the final one, the descriptions or comment of particular incidents. So this tweets, okay, is taken from 2014 to 2019. Why we start in 2014? Because that is the time where all the 6 prasarana, okay, starting from KTM, commuter up to MRT, okay, started their services. Okay, so the pre-processing of Manglish event tweets, okay, was performed using the proposed term standardization techniques. Okay, so we still use LDA, where we found that it is efficient in topic detection for both English and Manglish tweets, with better performance for Manglish. Okay, so the tweets, okay, are classified under several contexts. Okay, in our case here, we found that we can classify the tweets under service disruptions, the passengers etiquettes, okay, fees and payment methods, and conditions of trains and carriage. And there are some tweets, okay, that we classify under unclassified, okay, because there's so many terms that is not relevant to each other. Okay, so under the unclassified, okay, we tend to do more research so that we can at least classify the unclassified tweets. So this is a challenge that we are facing right now. Okay, so if you look at the previous research stating the issues, okay, in processing Manglish. So in this paper, we try to solve the Manglish tweets problems, okay, where you have different kinds of language in one tweets, okay, using term standardization with LDA. Okay, but the problems that we found, okay, that needs further research is that LDA mostly work on long terms, okay, meaning to say that, okay, if it's a blog or it's a forum, so it's much easier for LDA to work compared to tweets because the sentence allowed for tweets is just about 140 characters. Okay, so with short sentence, okay, LDA supposedly not to perform well, but we are looking into it on how we can actually enhance LDA so that it can perform as it should with even though the sentence short. Okay, so I think that is all from our group. Is there any questions? Please put up into the comment section so that I can answer later. Or if you have further questions, you can always contact me at myzatul@um.edu.my. Thank you very much, everyone, for listening. I think that is all from me.
Okay, thank you very much, Associate Professor Mazatul. Is there any questions from the floor? There is no questions, but I think we can continue the sessions. For the fourth speaker from Sunway Universities, I would like to invite Dr. Richard Wong Tek King, okay, to present his presentations on the topic predicting real-time traffic information for fast solutions. Dr. Richard, you can take over the sessions.
All right. Okay. Can everyone see the screen now? See the slides?
Yes.
Okay. Thank you. All right. Thank you, Dr. Badru, and good afternoon, everyone. So my name is Richard, and I'm working on this collaborative project between Sunway University and Universiti Malaya. And I have been working on this fog computing resource management for real-time travel planner together with my master student, Henry. And under this sub-project, we also have Dr. Yong and Dr. Badru with us. Okay. I have updated the topic of my sharing in order to match the focus of the work. And this slide is going to be a short presentation, short sharing, I'm focusing on just sharing the main idea of how the whole project works together. Okay. So, what is a real-time travel planner? When we travel from one place to another, most of the people, if not all, we will be using a kind of travel planner, such as Google Map or Waze, those we are very familiar with before we start traveling. And for us, the traffic information is very important, especially for us to plan our travel well in order for us to arrive on time, as well as to avoid traffic congestion. However, oftentimes we find that when we travel, the traffic condition actually change. If a travel planner is able to obtain the latest traffic condition of the area that is surrounding the device as soon as possible, then the travel planner will be able to update the most optimal routes for the users in real time. So when we integrate all these components together, we are actually looking at a real-time travel planner. So apart from the features that I have mentioned just now, as a real-time travel planner, the travel planner should respond in real time. That means we expect the system to have a low latency between the request and the response. And at the same time, as we mentioned that dynamic traffic condition is vital, we also want to obtain the traffic information of the area that we are in as fast as possible, as soon as possible, in order for the travel planner to update our route so that our route will always be the most optimal and to allow us to avoid the traffic congestion. Okay. So with 5G technology, we will be able to achieve this by deploying a mobile edge computing architecture, MEC architecture. So MEC architecture is a decentralized computing architecture where the function of a cloud server is shifted to auxiliary nodes. In essence, the traditional architecture for a travel planner is such that all the devices communicate with the cloud server directly. So regardless of whether we want the information of the local area or the information of the area from the other side of the earth, we are sending the request to the cloud. And this sometimes is very inefficient, and sometimes it causes high latency, especially when there is a lot of requests that needs to be processed by the cloud. So with MEC architecture, a device communicates directly with a node that is closest to the device. Some of the requests is able to be directly processed in the local node without the need to be sent to the cloud. And these nodes, they are also allowed to exchange information among each other. So when we apply the MEC architecture on a travel planner, we will have our user device in the vehicles, which most likely are the phones that we are using, connected to the nodes directly, as well as the traffic light, the speed cameras, also connected to the nodes in order to provide the localized traffic information. And the implementation of these nodes, which we call the fog nodes, they provide us with low latency due to the close proximity between the devices and the node. However, these fog nodes are normally having limited resources in terms of computational power. That means when we have multiple requests, multiple tasks coming in from different devices to a node, it is possible that the particular node will actually reach saturation and crash. This will actually cause a huge issue in terms of providing a reliable travel planning to the user. Another feature in the MEC architecture that I've mentioned is that the nodes, they are able to communicate with each other. Therefore, it is possible for us to offload the tasks to a nearby node in order for processing, in order to reduce the possibility of saturation. Therefore, we introduce the task distribution algorithm to optimally distribute the tasks by selecting the task to be offloaded to other nodes, as well as to select the node to offload a specific task to, in order to attain or to achieve low latency between the request and the response, and to achieve low energy consumption for each of the nodes. So this task distribution algorithm can be discussed using focusing on this node, on this particular node. Okay, this particular node. So first, the node will actually receive requests from the user devices. Then the node will predict the required processing power for each of the tasks and decide if any task should be offloaded. So if any task is to be offloaded, then the node will actually determine which task has to be offloaded to other nodes. So at the same time, it will also have to identify the nodes with available resources, so we know, so we can determine where the task should go. So in the process of developing the task distribution algorithm, we will incorporate machine learning and optimization, which are the two branches in AI, to achieve the different aspects of the algorithm. Machine learning algorithm is implemented in order to predict the required processing power for each task and to predict the occupancy of the nodes after offloading. This applies to both the nodes from which the task will be offloaded and to which the task will be offloaded. And the optimization is applied to devices in order to decide if a task should be offloaded, and also to choose or to select the node that we will offload the task to. So as conclusion, by implementing the machine learning and optimization technique in the MEC architecture, we will be able to optimize the resources of the nodes and improve the service for a travel planner. And at the time of this sharing, the master students is still working on developing the model, the simulation model, in order for us to further test and evaluate the algorithm for different parts. that's all from me. Dr. Badru?
Okay, thank you very much, Dr. Richards, for the presentations. I would like to invite the next presenter from Universiti Malaya, okay, Dr. Nur Jihan. She's going to present a topic on utilizing data anonymizations for protecting personal data applied to traffic monitoring system. Okay, so Dr. Nur Jihan, you can start to take over.
Okay, Assalamualaikum and good afternoon. So, can you see the slide?
I can see not your slide, your entire screen.
Okay.
Okay, now you can see.
Okay. So again, okay, thank you, Dr. Badru, for.
Sorry, this is your screen. I think you need to. Okay. Okay.
Okay.
Okay.
Okay, so I will presenting my research project collaborative data anonymization for privacy preserving vehicular ad hoc network. So me, Dr. Najihan, and then we also have Dr. Musin and our RA, Tarak Nandi. Okay, so his RA and also PhD students for Universiti Malaya. Okay, so the outline for my presentation today is, okay, I will focus on data privacy in smart transportation systems, which the first one, we will focus on the importance of data protections. And then okay, further, we will discuss problems that associated with data anonymizations. And then further, I will, okay, we will propose an enhancements of data anonymizations, which we propose a collaborative data anonymizations. Okay, so these are the common scenarios for smart transportation systems, which it shows that there is a vehicles, okay, usually for smart transportation system, the most important component is we have autonomous vehicles. Okay, so this, besides these autonomous vehicles, we also have normal vehicles where these vehicles communicate each other through inside via smart transportation system where these vehicles will send, it has a sensor, okay, autonomous vehicle has a sensor which later it will send or pass the sensor data throughout the entire network. Okay, so this communication between vehicles is known as vehicle to vehicles. Okay, so besides this vehicle to vehicle, we also have vehicle to infrastructure, where these autonomous vehicles has a communication between the another infrastructure such as smart parking systems and etc. Okay, so okay, based on this, okay, based on the importance of the common scenarios in smart transportation systems, there are possibility of several attacks that might occur in IoT authentications. Okay, so these are the some of the possible attacks that might occur. Okay, which is we have masquerade attacks, okay, man in the middle attacks, denial of services attacks, okay, forging attacks, okay, guessing attacks, okay, physical attacks, and routing attacks. So I'm not going to explain this further. So these are the possible attacks that might occur on IoT authentication. So basically, for smart transportation system, these are also the possible attacks that might happen. Okay. Okay, so because of this attack, so there is a need, okay, for us to increase the security and privacy attacks. Okay, so security and privacy are the most important aspects of the IoT network, including smart transportation systems, which it may include authentications, authorizations, okay, data protections, which it's usually involved with personal data, and then network security and also access control. So there is a need, okay, because of the importance of security and privacy. So there is a need to do further research related to these issues. Okay, so these are some of the techniques that we can use in order to protect data, okay, in smart transportation systems, where we have access controls. Okay, it is access control. It is a concept of authorizations, where it is related to what authenticated users are allowed to do for that activities. Okay, what we can do for that authenticated users. Okay, and then what is biometric technologies? It is the use of people unique physical and behavioral characteristics such as fingerprint recognition, okay, face recognition. So these are among of the biometric technologies that we use today. Okay, then besides that, we also have cryptography. Okay, it is a method of protecting informations and communications through the use of codes, okay, which only authorized users can process and read the informations that we send. Okay. And then the last technique is data anonymization. So these are the techniques that we are going to focus in this research. So anonymization, it is defined as a process by which personal data is altered, okay, before we send the data throughout the transmissions. Okay, so that data subject can no longer be identified that either directly or indirectly by any parties. Okay. So what is data anonymization? Okay, it has been defined as a process by which personal data is altered in such a way that a data subject can no longer be identified either directly or indirectly. Okay, so the main concerns of data anonymization is actually to prevent any sensitive information disclosure. So these are the three categories of information disclosure. We have attribute disclosure, okay, identity disclosure, and inference disclosure. So these are the three main categories which was the main concern why we need to prevent this kind of information. Okay. Besides that, there are also several anonymization techniques categories, such as generalizations, okay, suppressions, okay, distortions, masking, and swapping. So these are the categories of anonymization techniques. Okay. Okay, so these are examples of several types of data anonymization techniques. Okay, where we have K anonymity, L diversity, okay, T closeness, and noise addition. So I'm not going to explain this, but this is basically the main or the existing techniques exist for data anonymizations. Okay, so what motivated me to do this research is data anonymizations on traffic management system is an emerging topic because we are moving towards smart-based system. So anonymizing data is important. Okay, and then to enhance the current security and privacy needs, and also required in smart transportation systems. And we also want to explore in more details, okay, regarding data anonymizations, okay, besides privacy preservations and threats protections on personal data. Okay, so basically the problem statement, okay, is currently most of the previous works are dependent on a static and robust data sets. However, the data anonymization should be experienced with more dynamic and runtime data set, which is usually related with smart transportation systems data. Okay. Furthermore, previous researchers are mainly based on the local data anonymization systems. Okay. However, the necessity of the data anonymizations in VANET network is hardly identified. So that's why the local data anonymization is not enough for this kind of VANET network. Okay. So in addition, okay, collaborative data anonymization is got less attention. So that's why that's the main reason for this research. Okay, so the main aim for this research is to develop a model for the usage of the data anonymization based on privacy preserving system in smart transportation system for securing from current threats in the network. Okay, so the research question is what are the most effective ways in order to introduce the collaborative data anonymization techniques for smart transportation system? Okay, so this diagram shows the model scenario with our proposed solutions. Okay, so basically in smart transportation system, VANET ad hoc vehicle network, okay, VANET scenario, usually we have a local vehicle considered as V, and then we also have the X, Y, and Z as the neighboring vehicles, and M and N is considered as non-neighboring vehicles to V. Okay, so this is our model scenario. Okay, so assuming that these red vehicles, okay, want to send a sensor data to these orange vehicles. Okay, so there are some personal information that might included in this red car, such as driver's ID and etc. So the first thing is, okay, the information is obtained. Okay, so these are the data set for that red vehicle. Okay, then later it will be encrypted. Okay, and later will be anonymized in a table. Okay, so it will be anonymized the data to another receiver. So in that case, okay, this orange vehicle, so these are the data that this vehicle will receive from the red vehicle. So the process shows that we have the normal data, and then we will encrypt the data, and then later on we will anonymize the data. So the neighboring vehicles, which is the orange vehicle, will receive the anonymized vehicles, no, anonymized informations. Okay. So these are the flowchart for the proposed models. Okay. Okay, basically, start, okay, check status, okay, if it is a request to share the data. If yes, then we will perform data anonymizations. And then if it is safe to share, then we will encrypt the data. Later on, we will share the data. So these are the basic, our proposed model. Okay, so this is the proposed solutions for collaborative data anonymization techniques, which is, it consists of 6 steps. Okay, the first step is to request broadcast. Okay, vehicle V, okay, it is a local vehicle, try to collaborate with others and want to form cooperative data anonymizations. Okay, so therefore, a broadcast to all the neighboring vehicles, which is X, Y, and Z. Okay, so the X, Y, and Z, it is a subset of number of vehicles to participate and send their anonymized encrypted versions of the informations. Okay, then, okay, vehicles will identify the sensitive data, which is, it can be primary or it can be secondary, or and entities identifier on their own data sets. Okay, and then vehicle and V, okay, sorts all the primary identifier and then uses secondary identifier to establish a unique constraint. Okay, so next, okay, the send identifier will be used to form each EC. It is a subset of EC. Okay, then the next step will continue with initializations. Okay, if neighboring vehicles satisfied with the locally anonymized data, okay, then it will encrypt the data with using symmetric key cryptography. Okay, and then step 4, which is EC establishment. Okay, vehicle V, local vehicle, will receive all encrypted, okay, all encrypted data, okay, from its neighboring vehicles. Okay, later, okay, vehicle V, okay, local vehicle will decrypt all the data. Okay, and then step 5, okay, final anonymizations. Okay, vehicle V checks whether the anonymity level by examining the ECs. Okay, if the vehicle V finds that the dataset is designed with insufficient anonymizations, then it will perform the further process to the whole dataset as local anonymizations in step 2. So it will proceed to the second anonymizations. Okay, moreover, the vehicle V concentrate on the I diversity and T closeness. So it is where we combine I diversity and T closeness in these steps. Okay, then the last step is collaborative agreement. Okay, vehicle V later needs to encrypt the final versions of the collaborative anonymized dataset. Okay. Then now, okay, T is now broadcast to all neighboring vehicles. Okay. So these are the proposed solutions for collaborative data anonymization. Okay, so what we obtained from the previous collaborative data anonymizations is, okay, privacy preserving analysis. All the personal data, okay, entirely depends on the capability to protect the personal information. Okay, and then the sensitive data are fully anonymized locally before we transmit the data. And then the use of symmetric key cryptography, where all the information must be encrypted before we transmit the data. And then neighboring vehicles can easily identify if there is any alterations happen during the transmissions. Okay.
Dr. Nagian, you have 1 minute to conclude your presentations.
Okay, in terms of environment analysis, so basically when we involve in smart transportation system, we transmit lots of personal information. So therefore, the vehicular network environment needs a robust data anonymizations to protect data from breaches. Okay, for collaborative analysis, okay, the use of local data anonymizations may have a shallow effect on k-anonymity due to the volume of data. So, because basically in smart transportation system, we have a large data sets. Okay, a collaborative agreement that we propose ensures the group utility in the proposed scheme. Okay, in terms of precision analysis, okay, the proposed data anonymization techniques use only anonymous and encrypted data to transfer over the VANET network. Okay, every vehicles can ensure the data modification by the help of the designing structure of the procedure. So these are the explanations and the discussions for the proposed methods. Okay, as for the conclusions, the focus of this research is to preserve privacy, security in smart transportation systems. And then we have proposed privacy preserving collaborative data anonymization techniques. Okay, the analysis of the proposed techniques shows the practicality and feasibility of the schemes. Okay, so these are some output obtained from this grant. Okay, we have 2 journals, okay, conferences, and we have submitted 1 copyright. Okay, some references. Okay, so that's all from me. Thank you, Dr. Badrul.
Okay, thank you, Dr. Najihan. Okay, we're going to have the last presenter from Sunway University. But before that, if we do have some questions from the floor. Okay, there is no questions from the chat. Is there any questions from others? If not, and I would like to invite Professor Yao Kot Lim from Sunway University to present his presentations on investigating an energy efficient cognitive radio-based communication system, 5G communications. Dr. Yao, Prof. Yao, you can take over the sessions. Please unmute your mic.
Sorry, can you see my screen now? Yeah.
I can see your screens.
Can you see the full screen of my slides?
I can see, yes, definitely.
Okay, thanks. Thank you. Thank you, Dr. Baru, and thank you, everyone. I think I'm not going to spend long because I don't want to spoil your lunch. All right, so what I'm going to discuss about is actually an extension from what Dr. Rafida had presented, but I'm focusing on the proof of concepts for the 5G based communication systems, which is also based on the cognitive radio. So this work is from me and also Dr. Rafidas from Malaya, and students Muhammad Kazims and other researchers from Universiti Malaya. All right, so these are what I'm going to cover: introductions, a test bed, a summary of results, and finally conclusions. So 5G enhances the network performances, particularly the high quality of service, like ultra low latencies, about like 1 milliseconds at most, and then high throughputs like 20 gigabits per second, high reliability, better network connectivity with lower network congestions, larger coverage from 40 to 60 kilometers, and also handle a massive amount of data transmissions and heterogeneous devices. Now we can imagine the next generation's network is going to be, to be innovated with different kinds of new applications like driverless car, virtual reality, and they are generated from heterogeneous devices, from vehicles to laptops to smartphones to any other new devices. So it's a very different scenario than what we have today. So unfortunately, there is lack of investigations of networking schemes over networking test bed, particularly in 5G. So we can see that existing test bed basically uses some single processing units, which I'm going to show you next. But we are going to break the traditions and we're going to come up with some new form of test beds. All right, so we have test beds with a single processing unit, which is shown at the left side. And this test bed has a single processing unit whereby you can see that the dotted lines are actually the wired connections, and you have a switch in the middle, and this switch is normally connected to a centralized entity like a macrocell base stations. So, and then the networking entities will communicate with each other using wireless communications media. All right, so this is a very simple scenario whereby it is widely used. Why? Because it's simple. And imagine if you have every single nodes communicate with each other fully using wireless media, then you will need to have a computer attached to each one of the distributed entities here. So what we use in this research is basically to use a test bed with separate processing units, whereby each one of the entities or distributed entities here now is embedded with separate processing unit. Particularly, we use the Raspberry Pi. Of course, the Raspberry Pi is not very advanced, and it has its shortcomings, but this is the best that we can have off the shelf. And of course, we are going to see how it actually performs under such circumstances. All right, so you can see that for the test bed with separate processing units, we don't have the dotted lines connecting to the centralized units, and it's fully distributed, which means both control and data messages are exchanged over the wireless medium. So the advantage of our test bed is that we can actually enable the distributed nodes to make decisions independently, so that we can have two types of routes in the network. So the first type of node is called the backbone route, whereby the communications will need to go through the macrocell base stations, which is the key base station. And this macrocell base station is actually, it's not I, but it's A. It's macrocell base station. It's actually accessed by all different nodes, distributed nodes, and it can actually get congested easily. So, and it also uses licensed channels, whereby it doesn't have other unlicensed or licensed users activities. And the backbone route is basically used for performance enhancements, but it can get congested if there are a lot of traffic going through the macrocell base stations. Now, the other types of route is called the D2D route, or device-to-device communications route, whereby it aims to offload the traffic from the macrocell base stations. And it uses unlicensed channel, like what Dr. Rafida had explained. It's pretty much like a cognitive radio systems, and it's actually access the underutilized licensed channel in the network. And the D2D will enable direct communications between two nodes without going through the base stations, and hence it allows you to offload the traffic from the macrocell base station. Of course, it improves the performance. Okay, so we look at these two diagram here, and the upper one is basically the single processing unit approach, while the lower one is using the separate processing unit approach. Now, for the single processing unit approach, we have the PC, which is the centralized entity to process right up front and then the rest of the time it doesn't process, and it's just informed the rest of the nodes to perform accordingly. But for our separate processing unit system, we have every single nodes, including the centralized and distributed nodes, to make decisions themselves, and then needs to use the Raspberry Pi to process, and hence you can see that the processing time increases in our case. Now, if you look at the timing, particularly the access, read, and write time for the Raspberry Pi, it incurs higher time, and it's therefore causing higher delay in the systems, right? So this is one of the nodes in our test bed, whereby we have USRP, Universal Software Radio Peripheral, like what Dr. Rafida has mentioned. It's basically software-based. It's fully software-based. And we do have IP3 or the Raspberry Pi, which actually serve as a mini computer at each node to make decisions that enables every single distributed entity to make decisions. And it's, of course, make this test bed closer, a step closer to the real scenario. And this is our test bed, and we basically have got a control plane here. You can imagine this is one of the roadside units, and then you have the vehicles or the parked vehicles on the road, and the source node would like to find a route to the destinations node. So this is what we have done so far, whereby we have run this in a lab environment. Of course, we want to extend it to the real world situations. So this is basically our test bed, and if you compare our test beds is comparatively more enhanced compared to what we have in the literature, with more number of nodes and also higher number of device-to-device links, and also a scenario with heterogeneous nodes. And this is our results, and I'm just going to show you these results, one of the many results that we have, and it's basically comparing the software and hardware delays, and also the number of hops, and also the end-to-end delay, for 1 hop, 2 hops, until 5 hops. And we can see that the software processing delay is lower, and the hardware processing delay is higher, and the delays increases with time, with the number of hops, and also the centralized model is incurring lower delay compared to the fully distributed model, or the separate processing delay test beds that we separate processing unit test bed that we use in our implementation. And this is the number of hops and also the packet delivery ratio, and the packet delivery ratio decreases with the higher number of hops because of the interference and also the root switches and other issues. And this is a test investigations on the traffic offload, and we can see that the traffic can be offloaded from route 1 to route 2 to route 3, and also the backbone route. So the traffic offload is fully dependent on the ambient noise, and also on the licensed user activity, like what Dr. Rafida has mentioned, in cognitive radio system. When the primary user's activities exist, you need to switch your route. All right. So this is about the delay, and we can see that the delay also increases, and also increases with the delay increases with the number of hops, and also with the presence of the primary users. And for the backbone routes, which does not has any primary user activities, the delay is the lowest. Of course, the backbone route is good for improving the performance, but when the traffic is very high, when it becomes congested, then the delay will increase. All right. So in conclusions, the software processing delay is higher in separate processing units test bed compared to the single processing units, and the packet loss occurred in the licensed user activities reappear in all 3 D2D routes. Particularly, the traffic cannot be transmitted over the backbone route. It causes a lower overall packet delivery ratio. And the third point, cumulative end-to-end delay is higher in scenarios with licensed users activities due to the random reappearance of primary users activities and route switches. And finally, compared to the packet activity ratio, the licensed user activities have a greater effect on the cumulative end-to-end delay. That's I end my presentations. Thank you very much.
Thank you, Prof. Yao. Just sharp 15 minutes.
Thank you.
I think that ends our webinar for today.